NanoHub U, online instruction.
Hey everyone, welcome to lecture 219. So in this lecture, I'm actually going to summarize the entire Unit 2 and then give some brief conclusions. So if you recall, basically the point of Unit 2 was to talk about transfer matrix methods. And we started off with doing ray optical matrix methods. And so this is just showing an example of the types of ray optic transfer matrices that we considered. Now, of course, this is not an all-comprehensive list, but these are some of the elementary units like propagation through free space or cross dielectric boundaries, spherical boundaries, and lenses that we considered. And in general, we said that as long as we can represent our light as a ray, so in other words, it has a certain height and angle with respect to optical axis, and we're in the so-called paraxial approximation, or in other words, the angle is close to the optical axis, then we can propagate through many of these components in a chain using matrix multiplication and correctly predict the final output ray. But then we also said that that doesn't necessarily teach us about all possible situations. In particular, we could have wavelength scale features in our systems as well as periodicity in the transverse direction. And these kind of approaches can't really capture that sort of behavior. So then it was important to move to another method, which we call the S-matrix method. And then the point of the S-matrix method is not that it would necessarily disagree with the results of the previous method, but it's more general approach. But then it's also, as you can see, much more mathematically complex because we end up writing down either an eigenproblem with an unusual orthonormality condition, or we write down a generalized eigenproblem for what's called phi. And then phi was basically kind of one of the components that we use to write down the transverse H fields and E fields, which are written here. So this becomes like a fairly non-trivial task, in fact. So of course, I don't expect that you as the students would necessarily go through all the math and implement it like on your own code. But luckily there is like implementation already available. And we said that one implementation that you may be interested in is called S4. And so S4 allows you to take these layered structures which may have periodicity in the transverse direction and may have very thin and maybe very thick materials and sometimes very non-trivial materials. And then you can actually use this S4 sim tool available on nanohub.org. And then the nanohub tool actually adds some additional capabilities like a graphical user interface and builds in realistic materials. So it has a much more general kind of behavior and function. And then in order to validate this tool, we actually compared this not just to one paper in the literature, but many. But this is just one example, which is hopefully visually clear, showing that previous work on photovoltaic front coatings had mainly focused on using either one front coating layer and sometimes two, but this actually went up to 3 front coating layers. And it showed that as you add more layers, basically you get a better absorption in silicon, especially in the blue part of the spectrum. And so you may or may not be aware that a lot of solar cells actually look blue. And so this is actually like a physical manifestation of the fact that they tend to reflect in blue with just a single anti-reflection coating, which has this kind of absorption curve here. But then as we add more, then we actually suppress that blue reflection. And so it would actually look black at that point, which is actually better in terms of getting higher efficiencies than short circuit currents. And then we also showed that S4 Sim can basically reproduce this whole set of results on the right-hand side, and that it's very hard to actually tell the difference between the two curves, except that they're labeled differently and the thickness of the lines is slightly less on the right-hand side, right? But that's just a superficial difference. And then for more advanced applications, we actually talked about metasurfaces. And we said metasurfaces are a way to create light trapping in photovoltaics and photodetectors that rely on creating a phase shift on a very thin surface at the bottom of some semiconductor absorber or other absorber materials. And so then we actually showed that if you design these correctly and you essentially have a uniform phase front, then you can have light come in at one angle and then it can be deflected. So light is coming in normal and then it's deflected into a much different angle. And so that's illustrated as this +1 mode. And you can see what the reflection looks like here. So it's essentially a plane wave. And then you have enhancement of absorption in photovoltaics up to a factor of 10 at selected wavelengths. And then we also said that there could be other applications like for enhancing thermal emission at selected wavelengths. So just to kind of wrap up about these transfer matrix methods, we said the advantages are that they're applicable to a wide variety of problems. They allow you to treat layers which may be very thin and very thick in a computationally efficient way. And then that makes it computationally tractable on even machines with modest computational capabilities. It doesn't require a giant supercomputer. But there are, of course, disadvantages like with any method. So particularly certain types of problems can be more computationally expensive. So if you have very complex geometries, of course, which especially if they can't be well represented as periodic layered structures, if you have plasmonic systems, which have metals that create very large Fourier components, and then also looking at broadband types of problems. So in conclusion, it's a very strong technique, but we haven't necessarily looked at all the techniques that we'll need. So in the next unit, Unit 3, we'll really talk about something else that may be useful, find a different sign domain.